Stuff. So let's get started. Here we go. First with the agenda, which you guys always see, there's a couple new things on the agenda tonight to look forward to discussing. But first, let's jump right into what we always do about our website calendar. This is mostly for people that watch our presentations on YouTube and don't know much about the club. If you want to know what's going on with the club on a daily basis, please check out the website calendar, which is updated, according to weather, cancellations, postponements, etc. It's a great wealth of information for finding out what the club is up to. We also have a very active IO groups messaging board where you can find archived information or ask a question of your own. Lots of helpful folks. We're also active on YouTube, Facebook, and Instagram. There's a lot of good stuff that the club is doing, and you can check out social media to find out what those things are. Okay, is Jen in the audience? We shared a bunch of stories and experiences from the Grand Canyon Star Party
Jennifer
from last
contacted,
week.
Jennifer contacted me, and unfortunately, she's not able to join. So
Okay.
here's her surrogate. Put something up, and I'll tell you about her awesomeness.
Well, look at this first slide then, because this is something she sent me. There's one more slide, but if you want to talk about her images here, please feel free to do so.
She had the opportunity to go out to Hermit's Rest, which is a little bit out from where we normally set up at, and took her Sea Star out there. It's relatively new for her, but she was commenting about the cat's paw and the Omega Centauri cluster, and she just got, I mean, look at these. I'm only a little bit jealous of these video people and the quality that they get with such little setup. I mean, it's not quite what what you guys get with your true astrophotography, but just amazing things that we can pull in with this new technology and these little ones. And she took the opportunity to go out there and collect this stuff. Other than that, I'm not sure what her other pictures have, but she mentioned about how that she stayed in a hotel and had the luxury experience of a swimming pool and all kinds of other stuff that us in the campground did not have. But she sadly got to the Grand Canyon a little later than the rest of the San Diego group. And by the time she got there, it was packed on our little corner of the world. And she had to set up on the other side. And I told her I would mention how disappointed she was about that. So,
Man, what a great summary. There's one more slide coming up, but first I have to say, I did not realize these were Sea Star images. That's amazing. I mean, you're talking, she created these images with a toaster, right? Like, that's
yeah,
amazing. Here's the
yeah.
next slide.
Oh, and then the day that we went out with the solar astronomy and set up, hey, May, there's your logo is on a banner that I printed out for us. Okay, and set up out there for people advertising. We were showing them the sun there at the solar astronomy and talking to people about coming out to the main event at night. So during the day, we actually had some activities as well.
That's amazing. William, did you say that's another banner down there with our
Yeah,
logo?
that's a banner I made specifically for Jen for her solar outreach. We talked about getting together. I'm actually on the other end of this camera taking the picture. So yeah, I can make banners of that size almost without limit. The paper is the only real constraint that I have. Each those pieces of paper, and they are paper, not cloth or something more durable. Okay, but each of those pieces of paper costs about $1. But I can make them for the club for events, and happy to do it.
Awesome. William, thank you so much for not only doing that, but for summarizing these beautiful images. Thanks so much. Priscilla, tell us about the San Diego Dark Sky Festival last weekend in Julian.
Yeah, sure. And there are some other people on the call that were also there. So, I don't know, Craig or Jose, if you guys want to jump in, feel free. So, usually it was our club's event, but this year was just put on by a different club, and it was just one day. It was packed. They estimated about 1,500 people, and that was Saturday night. And yeah, I just saw your message, Zach. Yeah, there was some other SDAA people that tried to get in and they got stuck in the line and they gave up. They turned around. Um, but it was so crowded. It was like hard to even move a telescope around because there was just people everywhere. But the Milky Way looked great. It was a really nice night for seeing. Um, if you right behind, like if you can see, there's the guy there with the striped shirt. He did one of our meetings once, and he's like a young kid, and he has a 22-inch, and he was just putting it together there. Um, and yeah, anyways, that was fun being close to big glass, but it was, yeah, it was great. And I don't know, Craig or Jose, do you guys want to add anything?
I heard there was 3,000 people there,
Oh, wow.
but it felt like 6,000. It felt like 6,000.
Well, it felt like a million. I felt like people were
Yeah.
pulling on me, but
Wow.
Yeah,
What a great event.
I'm
Go ahead.
driving, but it was a fun event. A whole lot of people there, and it was great having solar telescopes for the daytime
Mhm.
to give people something to do. And then there was a lot to see at night, so it was nice. I saw M80 the first time I ever saw it over there in Scorpio, so I thought that was cool.
Awesome, you guys. Great summary. Does anybody else have anything to add that was there? If not, one of the things that I love about the San Diego Astronomy Association is that our mission is outreach. And I'm noticing that more clubs are coming into the game to do star parties over, a couple days events. And one of them that is coming up this weekend is the first time that this is going to happen in Big Bear, at least as far as I know. So the Bear Valley Astronomical Society is throwing their hat into the ring and holding Skyfest up in Big Bear this weekend. And what I really like about this event is they're going to have events all over Big Bear that kind of celebrate this idea of this, vacation tourist place in the mountains with a lot of stuff to do during the day that's not necessarily tied into astronomy or solar observing, but during the night is when they're hopefully going to shine. The weather isn't looking too good for it right now, but there are just tons of events, and I've noticed, unfortunately, that some of the events are even sold out. But there's going to be astrophotography lessons for both beginners and advanced users. There's going to be a big sky party. I think the big one is Saturday night. I'm not sure if there's one also Friday night, but the one Saturday will be at the Discovery Center, more on the other side of the lake near Fawnskin. So I'm going to go. I know some other members of the club are going. And what I really hope to learn, and maybe as a group, is to learn how to bring Julian Starfest, that is our star party, back bigger and better for next year. So if you guys are thinking about going to Big Bear, send me a text message or an email and let me know if you're going to be there, so that we can say hello during that event. Okay,
Be
we
really
have. Oh, go right ahead. Yes.
the Friday there is an event too. It's just at the top. You take a ski lift up to where that one is.
Awesome. I
yeah.
mean, there's so much that they're taking advantage of for the small little town that, during the winter is a huge ski town. And they
Mhm.
use the lifts even in the summer for mountain bikes, which is really fun. So hopefully if anybody's thinking about going, um, log on to the website and reserve your tickets, because I know it's through Eventbrite and a lot of the stuff is sold out. Like I think the Forest Sounds thing, Priscilla, both those things are sold out already,
Yeah.
which would be a really fun activity. But nonetheless, thanks for pointing that out, Priscilla. I think it's going to be a really fun event.
Yeah. I'll see you up there. Woo!
Yeah, see you up there. It's gonna be fun. Okay, folks, what we have next is Lucas Chen in the audience. Lucas was the winner of our senior division for the awards that the San Diego board goes to award. And Lucas, if you can get your slides lined up, Dave, are you on standby in case we need to stop sharing? to get Lucas going with giving a short presentation on his research.
As we
Right on.
talked, he's all good.
Thanks.
Nice.
Yeah, things are going pretty well. You can see the slideshow.
Yeah, Lucas, we can see it.
All right, perfect. Then I'll go ahead and get started. So, thank you everybody for being here today. I'm here to share my science fair project, which is called Evaluating Effective Waveform Analysis Methods for Minimizing Background Noise in Pulsar Navigation. So, first of all, let me share a little bit about myself. So here's a little bit to introduce myself. I'm going to be a rising sophomore at the Francis Parker School. So this was a freshman project of mine. This was a 9th grade project. And just a little bit about me, I'm really passionate about STEM in physics and astronomy. So I'm really passionate. I'm really excited to be here today. I'm also the founder of my school physics club. And I also do other things like I'm a competition pianist. I do creative writing and poetry, and I also do debate and public speaking. So a little bit to introduce this topic. So deep space travel is really difficult without Earth communication because when you're in space, it's really difficult when you don't have directions from Earth. So pulsar navigation offers one solution by determining a spacecraft's position based on detected pulsar directions. So pulsars are these highly magnetized, rapidly spinning neutron stars, as you might know, and they emit electromagnetic beams. And what's useful is because they're spinning so fast, it looks to us as if they're pulsing because the beam of emission is traveling rapidly. So we can actually detect that pulse, and it's very, very accurate. It's like an atomic clock. So we can use that as sort of an interstellar GPS. So that's the idea here. But a major problem, actually, I'm going to get like a laser pointer up here. A major problem with pulsar navigation is just there's so much background noise in space. So here's a graph from a project from a paper I've read and got here. So all of this here, these peaks, that's the pulsar X-rays you want to have. And if you look at here, it's about 2,000, but the bulk of the noise, the bulk of the X-rays, here we have about 26,500 X-ray noise. So the problem with pulsar navigation and why it's kind of more theoretical at the moment is because there's so much noise. So my project aims to kind of examine these different techniques for reducing noise and find what techniques are the best. So continuing introduction, I'm going to talk about a little bit about which techniques I'm using and how they function. So the first one is called low-pass filtering. So what low-pass filtering does is you set a given cutoff frequency, and then, as you can see, every frequency above that is just minimized. So you get to minimize all frequencies above a certain cutoff. The next one is fast Fourier transform. So what that does is that takes your input and it shows you a range of your frequency and how strong each frequency is relative to the whole signal. And then the final one, coherent detection, which I don't have an image for. You give it a desired signal. You say, this is the signal I want you to give me. And then based on another signal with noise in it, perhaps, it can pick out that reference signal. So onto the problem statement. So the general problem I'm trying to solve here is find what method of waveform analysis is the most effective to reduce this background noise in pulsar navigation. So kind of to narrow that down, because that's a really broad question, my question here is, how can you pick out this low frequency signal? I used 100 hertz. How can you detect that in the presence of strong noise up to 1 megahertz? That's 10,000 times more noise than signal. And so my hypothesis is when you have that low frequency signal with strong noise, the most effective way is using a low pass filter with that cutoff frequency near the original, and then when you use that FFT, that Fourier transform, you will see the frequency you want. So a bit more detail into methods here. Kind of want to look at my procedure. I also have a final goal project procedure because this is kind of like an introduction to the field. I'm not done with my project. But what I've done so far is, first of all, you generate that 100 hertz, 66 millivolt peak-to-peak sine wave signal that represents our pulsar signal. And then we also introduce this 10-volt peak-to-peak 1 megahertz broadband noise. So it's just we make this very, very small signal and we introduce a ton of noise. to represent what it's actually like in interstellar conditions. So you also run that through an adder box to combine the two, and then I conduct my research on that, taking different pieces of evidence. Different pieces of data. So let me show you my materials here. So I was able to use the UCSD electronics lab for this. So these are different materials and machines, more analog machines I was able to use for this project. So here's a waveform generator that generates our sine wave that represents the pulsar signal. And here's a noise generator that generates that noise. Here's really interesting. Here's a signal adder box I made. So this is a custom made piece. So I was able to solder a few wires together, and this combines our desired signal with the ton of noise. And then I also have here filter boxes, which set that cutoff frequency so you can filter out the higher frequencies of noise. And then finally here, I have two oscilloscopes, which are just used to view my signals, and then coherent detector, which is for the coherent detection part of the process. Also, something cool I wanted to share with you, because I was kind of using computational devices here and computers, I actually learned how to use Fortran for this project. So this is a simple program I made using the Fortran language in order to help me conduct my experiments and receive data. So here's just a quick overview again, experimental setup. It just shows how everything wires together. I have one channel that shows me just the sine wave, one that shows just the noise, one them combined, and then finally them combined and filtered. So it shows every step of the process so I can really see how each step works. Okay, here again is also, these are the points of data that I got, my experimental measurements, which I'm going to show you some analysis soon. So here, let's start with low-pass filtering. So these graphs show you how low-pass filtering works. So this is figure 1. It demonstrates how low-pass filter works on a sine wave. So this is the signal we have that represents our pulsar. You see, if you can see here, at points above our sine wave frequency, the sine wave is fine. It's not affected. But when you start setting your cutoff frequency too low, your tiny sine wave is affected, and then you lose your own signal. So what this is trying to tell us is that we shouldn't set our cutoff frequency too low, otherwise we lose our signal, which makes sense, right? So here we have our noise, which is telling us the next step of the process. We have a ton of noise in a tiny signal. How can we alleviate that? So low-pass filtering allows us to get rid of the vast majority of this noise. So because our signal is right around here at 0.1 kilohertz, what we want to do is set our low-pass filter around there so we minimize, in this case, up to 200 times the noise that we would have anyways. So that allows us to pick out our signal there. And then here, this final graph just shows us them combined. So if you look here, there's a tiny little bar here, little area where we still have our sine wave signal, but we've lost most of the noise. So that's step 1 of the process. But the next step is we have to look at fast Fourier transform. So while low-pass filtering is good as a pre-processing step, it doesn't really mean anything until we use fast Fourier transform to show us all the frequencies and find which one our signal's at. So this is a fast Fourier transform without any processing. If you look at this, it's just pretty much flat all throughout. That means our noisy signal is so noisy we can't pick out the signal we want. So instead, if you look at this filtered signal, once we've done filtration, you can clearly see this little peak here, which is exactly at 100 hertz. So what this shows us is that it shows us the success of low-pass filtering in eliminating noise. So before, you didn't see anything. Now you can actually find that signal. So this shows us we can, in fact, pick out that signal within a lot of noise. But the next question is, how does fast Fourier transform compare with coherent detection? So figure 6 and 7 here, they compare filtering in fast Fourier transform with filtering and coherent detection. So as you can see, they're pretty similar in performance here. They kind of stagnate after a while. But coherent detection generally has a more stable performance at higher frequency. But most impressively, both Fourier analysis and coherent detection remain usable. You can find that signal up to more than 10,000 times more noise than signal. And that's really impressive because in space, when you have a ton of noise, we can still pick out that pulsar signal. So because these differences are kind of negligible, we can compare these two methods through a more practical standpoint. So because coherent detection requires that you have a reference signal, it's like you say, here's the signal I want, can you find it? It's less effective, less practical, because in space you might not have that signal. Fourier analysis in this case would be more effective because it allows you to do that with any signal rather than you having to give it one. So in this case, that's why Fourier analysis is stronger. So we've come to a conclusion. So for interstellar applications here, we can see clearly that low-pass filtering with Fourier transform gives you the most effective results. So even though coherent detection is successful as well, it's less practical because it requires that reference signal in order to function. So let's go through a little bit of overview. Low-pass filtering reduces your noise up to 200 times. And then you can use low-pass filtering and Fourier to detect that correct frequency up to 10,000 times more noise than signal. And what does that mean for, what does that mean in terms of scientific research? What does that mean for our impact? So we can find our processing methods through this project. We find the best processing method to accurately detect a pulsar signal for more than 10,000 times more noise. So we've identified the ideal practical technique for extracting your weak pulsar signal when you have a lot of strong background noise. And so this is a really crucial step toward autonomous spacecraft navigation. What this means is that we're no longer restricted to our home here around Earth. Pulsar navigation lets us explore and discover the vast cosmos beyond. We can look through galaxies far, far away. I didn't mean to make a Star Wars reference, but we can look at very far cosmos and explore that without needing to communicate here at Earth. So some future work, just some notes. In future work, I would add some alternative noise reduction techniques to keep evaluating more techniques. And then in the future, I would, instead of using sine wave, which approximates a pulsar, I would use real pulsar data. And then I would also hope to develop a physical prototype model. Okay. Just some acknowledgements quickly. I would like to sincerely thank everyone here at the SDAA for the opportunity to present this research and just for supporting these student-developed projects. It's really helpful for me as a student to get recognized, and it's really encouraging for creating more research in the future. And then also the GSD-SEF, the Science Fair, for providing the platform for developing this project, and kind of my mentor slash guide for helping me with the electronics and for lending me his lab, Dr. Fred Driscoll. Last but not least, I would like to thank all of you here today for letting me share my project with you. So thank you very much. Appreciate it
We're
very
better
much.
for it, Lucas. Fantastic presentation, very interesting research. Who has questions for Lucas? Anybody?
Hey, Lucas, this is Ken. I'm one of the judges. Are we going to see you next year?
Oh, for sure. I'll be there. This was such a fun experiment. This was my first time here at a science fair, so it was kind of daunting at first, but once I kind of got into the groove of it, I found there's a lot of value and a lot of fun in scientific research. So I definitely think I'll be there at the GSD-SEF next year. So I'll see you there.
Yeah, we'll see you. Did you go to the state level?
I did not. I was not chosen to go to the state.
Anybody, any other questions for Lucas while we have him here with us?
Thank you, Lucas. That was an excellent presentation. Certainly better than I could do.
Thank you so much. It means a lot.
Hey, Lucas, I've worked along scientists my entire life, and I got to say, one of the things that really drives people not only to be excited about their research, but also influences them to possibly be scientists on their own in whatever, field they're specialists in is passion, which you clearly exude. So number one, on behalf of all of us, huge congratulations for this first place senior division finish. And we all wish you the best of luck in your endeavors. I can tell just by your energy and, quite frankly, showing all the gadget pictures made an impact on me. I consider my garage the Tony Stark garage, and it makes me want to go down there and build something after hearing your excitement and seeing all your fun pictures. So thanks again. Huge congratulations. You're going to make a huge impact in your career. So thanks again for joining us too. Really appreciate it.
Thank you so much, B.
You're so welcome. Thanks again. Hey folks, one more bit of business before we head into our main presentation. We have an election coming up and it is very close now. Please consider that the people on the board donate lots of times to get this club running, along with, the foundation that's newly formed. We need your help. So please consider the 6 seats that will be voted on in the upcoming election. We have 4 director positions which serve 1-year term. Obviously up for election every year. Along with that is my position, the vice president. This is a 2-year term, along with the corresponding secretary, again, a 2-year term. Dave, I've lost the ability to forward. Can you just forward the next slide if you're still there? And that is just a few things that you can reference later. I'm not going to go through them of what we're looking for. Most importantly, get along with people. I mean, there's a lot of stuff that we handle, obstacles that, obviously come up with a club this big and the things now that we're planning for the future. Please come in with, a good idea of where we want to go and how we get there when a lot of people may have different ideas. We have to find a common path to start doing some great stuff with the club. One of the great things is that we actually have our point of contact now that was assigned by the board our last business meeting, and that is Jerry Hilburn. He is the nomination committee person that will be doing the initial organization for the committee to come forward to start accepting applications, biographies, interest in these positions. So if you have questions about any of the process or what these seats are responsible for, please contact him or any other board members. We'd be happy to fill you in. Okay, next slide, Dave. I think we're at our main presentation. I am so pleased that Richard Wolff-Jacobson has decided to join us for tonight. And his talk is Historical and Modern Tools for Celestial Wayfinding. Hey, Richard, you're up. Please go ahead and share your slides and welcome.
Great. Thank you. And while I'm fumbling about here, great presentation, Lucas. You've given me some tough act to follow here. Okay, everyone see the presentation?
We can see it, Richard. Thank you.
Great. Okay. Well, thanks, Priscilla, for reaching out and inviting me, and for making this happen. I am Richard Wolff-Jacobson. I like to build things. I like astronomy, so I like combining those things here. You can see a photo of me and a star party there to get you excited. So essentially, this is a presentation that I put together as a result of some of my work around an open source project called the PiFinder that uses plate solving, and I wanted to sort of get a background myself on how we sort of came up with this and how we got there. And I ended up going much further back in the past than I originally expected to, and this is the sort of result of that. This isn't really a linear history. It's more an exploration of how human beings have thought about the sky, communicated about the sky, recorded positions in the sky, and ultimately what gets us to a point where we can find things in the sky and share those things with other people. So I'm going to talk about patterns in the sky as they've been kind of interpreted historically, how people have generated images of the sky, actual durable artifacts, how they started describing positions in the sky, ultimately how we started using computers to augment all of those things, and then I'll kind of round out with a little bit about how I pulled that together into what I hope is a nice observing experience. So let's talk about patterns first. And I start with asterisms, which are groups of stars that are, for one reason or another, they stand out as unique or distinct from other parts of the sky. Some obvious examples are like the 3 stars in Orion's belt, the Pleiades. Almost every culture that had access to this part of the sky saw those and saw them as a distinct sort of entity. Other cultures have also focused on the dark lanes of the Milky Way. We don't get too much of that nowadays, but they're very, predominant if you've been under a great dark sky. And so these asterisms are, regions of the sky that are recognizable because they're, they contain a grouping of bright stars, or they contain, they're in a void, and so they feel set apart. Once a culture starts communicating about these asterisms, these kind of unique areas of the sky, they build a lore or a mythology around them. So constellations take an asterism or groups of stars, and they apply shared kind of cultural significance to them and some amount of storytelling around them. They're often religious, and they have some, sort of interesting aspect to them, that humans would find interesting. People fighting or people exploring, something that makes them salient to the culture that they're invented by. And a lot of these end up being useful for things beyond just storytelling. They may signal when certain things can be planted, or when certain activities take place. They're recognizable, and these wayposts throughout the year often get incorporated into their cultural story. An interesting one that I found as I was kind of researching this is that the dark area in the Milky Way, which is more predominantly from the southern sky, it looks sort of like an emu if you squint, like an elongated bird. And when it is upright, standing about on the horizon, that is a good time to go and collect emu eggs. That's their nesting season. So this is the sort of lore that builds up around these asterisms and turns them into sort of salient cultural items. Of course, we now have a set of these constellations that were standardized. They incorporated a mix of Middle Eastern and Greek and Roman sort of mythologies. The International Astronomical Union defined these in 1922 as these 88 distinct constellations that we generally use today. For convenience, they sort of divide the sky up into even-sized parts, but we know there's a couple kind of oddball small ones and large ones in there. But that's sort of where we've ended up today, and what most people think of as our common set of language about describing regions of the sky. So not long after humans started communicating at all, they started drawing pictures, and pretty soon after that, it seems like we started depicting the sky itself. It's not clear exactly when this might have taken place for the first time, but the Lascaux caves in France have some interesting paintings that seem to depict some aspects of the night sky. And here you can see someone's attempt to sort of map some of these dots and other arrangements of imagery into the night sky. This was 19,000 years ago. And we have some much stronger evidence, more recently. This is still something like 5,000 years ago, or about 5,000 years ago, the Babylonians started, depicting the night sky in ways that we would absolutely understand and recognize as such. This tablet is from 3,000 years ago, so 1000 BC, and it shows constellations identified as meaningful to the Babylonians, and rise and set times for certain stars at certain times of the year. So this is sort of a combination of a pictorial representation, but we also start getting some data gathering and sort of tabulation. The Egyptians did a lot of observation, and they used astronomy and both for navigation and for other calendar purposes. This is a great example. A little over 2,000 years ago, it's essentially a planisphere as we would recognize it today. The constellations are different, but it's laid out the same way. We have the cardinal directions. We have the sky as it might look at some time of the year. The Greeks spent a good amount of time systematizing a lot of knowledge. This particular image is from a work by Ptolemy called the Almagest. This was the astronomy textbook for almost 1,200 years, and it divides and sort of defines a little bit of the modern constellations that we see. It's only got 48, but a lot of the basics are there. It's got some beautiful images of the sky. But this was sort of a through line that had a sort of schematic and descriptive view. But there were other ways of representing the sky as well. This one is from the Islamic Golden Age. They did a variety of very sort of ornate, sort of more artistic renditions, but also some very schematic sort of diagram, information dense works of art as well. The Renaissance generated an enormous amount of art, and you got a lot of interesting representations of the night sky. They were often focused on astrology at this point, so it wasn't quite so much a scientific study. They weren't trying to describe exactly what the sky looked like, but it had a lot of narrative around the constellations, and you get these beautiful tapestries and so forth. Eventually, we came up with mechanisms for actually recording what the sky looks like. Photography is the primary way that we can do this in a very specific way. The first known photograph of the night sky is this one from 1840 of the moon. Probably about what those astronaut trainees are taking from that balloon, I guess. But you can see that it is a representation of the moon. You could sort of recognize it. It's a start. Not even 40 years later, though, people were starting to take photos of dark sky, deep sky objects like the Orion Nebula. And you can sort of see what this might have, looked like through a telescope at the time. This was taken through an 11-inch scope. And it probably is a fair representation of what that might have looked like. Not too long after that, just a few years, we got this example, which is much more refined. It's a larger scope, better emulsion. They've really been pushing the envelope. And what's interesting about this is one of the first photographs that showed more than what you could see with your eye. There's stars here that were invisible, even through a very large telescope. It sort of highlighted the power of collecting more signal over time. And it really launched a much deeper sort of exploration of the night sky than you can draw or even observe directly. This sort of culminated at the peak of chemical photography in the 1940s, 50s, 60s, 70s. The Palomar Observatory Sky Survey is a great example of kind of the state of the art there. Large plates, glass plates, exposed, with really fine emulsion, great captures. I still use these images from the Sky Survey myself because I feel like they're good representations of what modern amateur telescopes might produce under a really dark sky. So the Palomar Sky Survey was notable because it did catalog essentially the entire sky that was visible from that scope on plates, 1,900 of them through a 40-inch scope. So it really was at the time the best picture of the night sky that we were able to produce. Well, since then, we've become just sort of enamored with these incredible images that come out of new digital sensors and new signal processing techniques. So, there's not much more to say here. We've seen a ton of these. They're fantastic. They're both, deeper in terms of the magnitude that they can go. They're narrower. We have, better magnification. Just everything that we would want out of a photo of the sky, just, turned up to 11. And we've got some great sky surveys that have now taken photos of the entire sky in collaboration with various telescopes. And, not more than 160 years after the first photograph of the night sky, we now have things like the Gaia data set with 1.8 billion stars down to, I'm not even sure, I don't have a note here of what the magnitude is there, but far more stars than we could ever hope to see and record by hand. We now have access to in a data set, which is, I think, pretty incredible progress for the last 160 years. So soon after describing the night sky, both verbally through constellations and ultimately drawings and other artifacts, there became a need to try to describe the relationship of stars. How far are they? Where are they? How can I tell someone else how to find this thing? And so some of the early attempts at this, one of the earliest was, again, the Babylonians, keen observers. They developed a system based on the ecliptic, so the path of the sun through the sky, and what constellations that they had that it traversed. And so they essentially sort of started this whole astrology thing with a particular set of constellations along the ecliptic that they felt were meaningful. And so along with that, by about 750 years before the Common Era, they were also using degrees as a measurement. So, divide a circle into 360 of them and start describing distances between objects using degrees. The Greeks, refined everything about this considerably. They had a good amount of time to work on it. They imagined the stars and most things in the sky as part of this sort of sphere that was sitting outside of the Earth. And so they essentially started mapping coordinates from the Earth by projecting them onto this sphere. And they came up with essentially the right ascension and declination system that we use today. Along with, inventing a new sort of coordinate system, they cataloged over 1,000 stars. Again, this is in that sort of textbook that was existing in the ancient world for over 1,000 years, the Alchemist. And they had pretty good positions for these 1,000 stars. They're not great by modern standards, but they're surprisingly good considering the tools that they had to measure distances in the sky and observe these stars. We've extended our understanding of position now with a time component. We understand that these stars actually move relative to one another in the sky, and we've been able to measure the distance from us to these stars. So not just their apparent visual separation from one another, but how far they actually are from us. So we have a much richer understanding now of stellar positions and these coordinates. And yes, we still use right ascension and declination with proper motion and parallax, but we can also now understand stars where they are in a galactic sort of frame, which is pretty cool, I think, at least. And so that's kind of where we've come to date with coordinates. Once we started compiling these enormous sky surveys and getting really fine-grained in how we can describe positions, we generated a lot of data. So 1,000 stars, in a textbook is great. 1.8 billion stars is almost too much of a good thing. So computers really help us sort of make sense of this. And they're used all over astronomy, but I'm going to start focusing in a little bit on, again, wayfinding. So how people describe things in the sky and communicate that and find objects. One sort of computer it's a mechanical computer or setting circles. We've probably all gotten familiar with those from early telescopes that we may have had. You polar align the scope, you set the dial so that you are properly aligned with the local time, the local sidereal time, and then you can dial in by moving the scope into a particular set of coordinates, and you can find objects from a table that's provided or someone tells you where to find them. It's a good solution. It was the standard for a long time. It requires careful polar alignment, and you need to continually adjust the coordinate frame because the sky is rotating overhead, and you need a really fine-grained scale if you're going to get really accurate. So you can see at top we have a pretty well manufactured scale. At the bottom we have a not quite so good scale, and you can imagine you'd have some difficulty finding the difference between two really close galaxies with that. But this was the way to find objects for quite a long time. Computers allowed us to do more sophisticated things. So we introduced these digital setting circles. If you're really nerdy, quadrature encoding is kind of the workhorse technology here. And it lets you determine whether a shaft is rotating one way or the other and how long, and it's digital, so it gives these sort of pulses that are really amenable to computer analysis. So this is a way to tell how the mount that your telescope is on is moving, but it doesn't really tell you where you're pointing in the sky by itself. So the big innovation here that computers allow us to do quickly is to take one coordinate frame, the right ascension and declination, and map it against the sort of motion of the telescope frame by lining up a couple key points, 2 or 3 bright stars normally. And once that's done, you have a pretty good idea that when the telescope moves this way, you're going to get a different part of the sky, and you can predict what that is using this sort of mathematical transformation. So we've all used that. They work to various degrees, depending on how good your alignment is and how solid your scope is. But it is an indirect way of determining where the telescope is pointing. Computers also enable a much more direct way to essentially take an image of the night sky taken by a camera and positively identify exactly the coordinates at that center or any point in that image, and that's plate solving. The plate is from the photographic plates that they used to use, and people used to do this by hand, lining up plates to try to map right ascension and declination from one plate to the next and solve positions of various stars. We can do this now with the help of computers. There's a ton of ways to do this, but the great thing is that it's direct and it's observational. So it kind of gets back to, someone looking at the night sky, knowing exactly where they're looking, and it's a little less abstract than we got eventually with these setting circles and ultimately digital setting circles. So it's very accurate. There's different algorithms. Some are faster, some are more accurate. But it's a really useful technology. And I think I want to talk a little bit about how plate solving and our modern technology can kind of pull all of this together. And so patterns, pictures, coordinates, computers. I'm going to talk about my open source project here. It's I hope interesting to the group, and it's something that I would encourage people to dig into. You can find all of this online. You can build one of these. So the PiFinder is an all-in-one plate solving finder, essentially. You put it on your telescope, it takes photos of the sky, tells you where you're pointing, has a catalog of objects. If you select an object, it tells you how to move the telescope to get there. Because it uses plate solving, it's very direct. It doesn't have any of the uncertainty of digital setting circles. And I think it's really a combination of all of these sort of activities that humans have done throughout history. And I think it enables a sort of nice return to observational astronomy. I'm going to talk a little bit about the methodology behind plate solving. I'm going to go through this pretty quick, but there's a lot of interesting information here. But I think it kind of weaves the same line of observation, picture taking, coordinate description, and then ultimately positioning. The first thing that you do to plate solve is you get an image. The second thing you do is you try to find the stars in that image. For a computer, an image is really an array of pixel values. There's a lot of data there that's extraneous. You have noise and you have signal. So the process of detecting what is a star and what's not a star in an image is generally called centroiding. It returns a list of coordinates in the image and hopefully a brightness. So you can see that here where we've sort of had the centroiding run and pick out all the stars from this image. And then you feed that into a solver. And the solver I'm going to describe here is one that the European Space Agency uses for their satellites, or at least they did at one point. And it's interesting because it doesn't need any hinting at all. It essentially is a blind solver, lost in space is what they call it. And it was to make sure that if their satellites got out of orientation, or they wanted to verify the orientation of their satellite without any prior knowledge, they could take a photo and understand, both the right ascension, declination, and roll, essentially of that telescope. They release this open source, which is great, so you can dig into that. It's really interesting. But it starts by taking a list of these ordered centroids. And you can see here, I've kind of highlighted how this centroiding becomes a sort of robust data set for the solver. I could have put a table of stars here, but I thought this was a little more interesting. Once you have these really isolated stars, very specific coordinates on the image, you can start building a pattern. And the way that the Tetra 3 solver approaches this is by picking the 4 brightest stars in the field. It then takes the closest of these 2 stars and it determines a distance, d, we'll say. Then for each one of the combinations, so every line that you could draw between these stars, it measures that line as a multiple of d. And it's always going to be positive because it started with the the closest set of those bright stars. And you can see here that, you get quite a bit of these edges that are connecting these stars and their distances between them. Once you have that, you can abstract this even more. You can boil this even back further to just the string of distances. And you can put them in a specific order that's determined by the brightness. But essentially, you get this list of numbers that now describes this pattern of these bright stars that you extracted from an image that you ultimately took with a camera. So we're sort of filtering this data and making it more approachable for computers with each one of these steps. The nice thing about this string of numbers or hash of this pattern is that this pattern will generate the same string of numbers regardless of how it's rotated or how big or small it is in the image. Because you're measuring based on the distance between the two stars, you always get this same thing. So it's invariant to rotation and scale. And this hash can then be, really quickly and efficiently compared against a list of other hashes, other patterns in the sky. So you find one that matches, and that identifies exactly where this plate was taken. There's some verification and some other sort of fine stuff to reject false matches and so forth, but essentially that's it. Develop this pattern, get it to a number, compare this number with a list of a lot of other numbers, and when you find the one that matches, that's where you're looking in the sky. So how many of these patterns are we talking about? Well, the particular database that the PiFinder uses, and it's got about a 10-degree field of view, and it's based on stars down to magnitude 7, which is what we can expect to get from the camera and the sort of exposures that we're hoping to use. That database of 118,000 stars and a 10-degree field of view, you need some overlap and so forth. So there's some interesting stuff about how you determine, where to grab these patterns. But that generates 712,000 patterns. The magnitude 7 was selected because you can get to magnitude 7 with a sensor that we use in, about a fifth of a second, sometimes less if you have a really dark sky. And so that lets you kind of get this exposure and this solve, which takes only 17 milliseconds to develop that pattern, search through all 712,000 of these. So you can do that many, many times a second, at least 5, sometimes 20 times a second. So you get really kind of almost real-time pointing information about where your telescope is pointing. So that's how I've decided to use this sort of history, this rich history of describing the sky and communicating about it, taking images of it to enhance my observational time. I hope that it can enhance other people's observational time. And so this is the end result of what finally got me started on this exploration of how people have been describing the night sky. That's the end of my presentation. I'm happy to take any questions here. I haven't been looking at the chat window, so if anyone dropped any there, I'll take a quick look. But I'm happy to answer any questions about the history as I did a quick skim of it, or the PiFinder or the algorithm. I'm happy to talk on any of those.
Anybody feel free to unmute and ask questions as you feel like it.
I have a question.
Yeah.
Okay, so you kind of talked about history of kind of observational astronomy. Where do you think we're going now, like future? Where is our current trajectory at?
That's a good question. I expect that every member of this club would probably have a different answer. So I love visual astronomy, and I don't know where astronomy as a whole is going. I mean, the science is reaching ever deeper, ever broader wavelengths. That's all great, but I think from an amateur perspective, people are doing more and more imaging, which is great. I hope that doesn't displace visual astronomy. And so one of my desires with the PiFinder project is to make visual astronomy a little more approachable for people. Star hopping is great, and I encourage people to learn the night sky, but I think people who are approaching visual observing need some wins to keep their interest going. And so I think, making an approachable system that people can use, and maybe it can guide them. I think there's some interesting things that can be done with like collaborative stargazing, because we have a computer, and theoretically we might have an internet connection, so you can do these things where people who may not have a local club could get advice on what to observe. They could join virtual star parties. I think that's the future, at least the near term future, that I'm kind of focused on and excited about.
All right, thank you very much. Great presentation.
Oh, thanks. Yeah. So, how is the PiFinder orientation with relationship to the telescope determined? Fantastic question. The PiFinder sees 10 degrees. So that's 20 full moons across, basically. If your finder shoe is at all kind of pointing in the direction that your telescope is pointing, and you put the PiFinder in there, your telescope will be looking somewhere in that 10-degree field of view. But the question is where. It's looking at a half a degree or a quarter of a degree. So to tell the PiFinder where in its 10-degree field of view to put objects when you want to push to, you just point at any bright star and you select that same bright star on the PiFinder screen. So it'll show you a star chart with constellation lines, and you essentially use the arrow keys to select the star that your telescope is pointing at. That's all that it needs to understand what pixel on the sensor represents the position of your telescope. And if you ask it for like, M80 or something like that, it will give you push to directions to get M80 at that particular point on the sensor. So therefore it's under your telescope, your field of view. Yeah, in this image, describe the components. Great question. I might jump ahead to, okay. Here's an early version of the PiFinder, maybe. It's got its kind of fell off. So there's a camera, of course. It's smaller in the recent versions, but this was an early prototype. It's got a little computer in there, a Raspberry Pi. It's got a keypad and a screen, and all of this runs Python software on Linux. And it does the heavy lifting of solving and exposing, and essentially just presents to the user a menu system that you can select objects and so forth. So if we go back to the form as the PiFinder looks now, let's see, there we go. You can see the camera. There's 3 different sort of configurations here for different types of telescope, but the camera is much smaller. But we have the same screen, the same keypad. And this is a sort of Vixen style dovetail that you can, mount in your scope. Other questions?
Can you tell me the form factor and the weight?
Sure. So that's a great question. I'm trying to think of something to compare it to. So it weighs about the same as a Telrad with the battery, a little less than a Telrad without the battery. You can build it with a rechargeable battery or without a rechargeable battery. It's this size, I guess. Here's my hand. So it's not, exceptionally large. It's pretty easy to fit on most scopes. It's not especially heavy. Again, it's like a Telrad, less than like a 9x50 right angle finder. So if you can, support that at the top of your telescope, you can probably plop this in and have it work. It does mean the screen is a bit small, so you can mirror that on a larger tablet or phone. You can use Sky Safari. I find it fine with my readers, but I gotta put my readers on to use it at the scope.
Does this come fully assembled in kit form and so forth?
Yeah, so you got some options. Thanks, great question. You can just build it yourself. All the plans are online, a list of parts. They're all pretty available off-the-shelf parts. So if you want what I think is a fun project, and you've done even a little bit of electronics work, I think it's really approachable. It uses all large, hand assemblable components, and you can just have at it. If you want to buy a kit, that's great. Makes it a little easier. I collect up all the parts and I can send them your way. If you have a 3D printer, you can 3D print the parts, or you can get printed parts. And thank you, Christopher. And if you want a fully assembled unit, I have those available as well, and they look like this. The build it yourself ones look a little different. They function exactly the same, but they're designed to be built by hand, whereas this one is a little more actually it's slightly larger than the build it yourself one, but it's just designed a little differently. It's not quite as easy to assemble. So
Richard, what filament do you recommend for the 3D printing?
yeah, so if you're gonna have anything that's outdoors at all and is exposed to the sun, you're gonna want something a little more robust than PLA. I use a PETG blend. It's nice because it's temperature resistant up to wherever humans would reasonably be comfortable. You can leave it in the car and it won't melt. And it's pretty robust strength wise. I've been producing these in various forms for about 3 years now, and so there's hundreds in the field, and we've refined the design based on feedback, but the PETG seems to stand up pretty well.
Great, thanks.
Joel Martin, it looks like you have a question.
Yeah, my question was, does the hash code derived from 4 stars always work? I think what you've done is really cool, and the algorithm is really cool because my ASI error fails with 50 plus stars. I really need a wide field of view. I mean, you obviously have a wide field of view, but still, it's very slick.
Oh, thank you. The 10-degree field of view does a lot of heavy lifting here. It lets you get a lot of bright stars pretty quickly. As you get narrower and narrower, you need to go deeper and deeper to get sufficient stars. You start getting more and more patterns. You start getting into instead of 100,000 patterns, millions of patterns if you start talking about less than a degree field of view. So the sort of plate solving that astrophotographers use and need is a different, not an entirely different beast, but there's a lot of constraints along with it. So for visual astronomy, this will get you within a 100th of a degree. So it can identify 2 different images that have about a difference of 100th of a degree. For astrophotography, that may not be enough though to get multiple exposures to align well. So it's a challenging bit of work. But yeah, for bright stars, the solver that the European Space Agency produces, you can tune it so you could say use 6 bright stars instead, but 4 generates a lot of connections between them and seems to do a really good job. There was a question about demo and usage videos. I am not good at video production, so I have not produced any, but there's a couple YouTube reviews that I think do a good job of sort of showing the workflow. And it's perennially on my to-do list. So if anyone's good at video stuff and wants to contribute to the project, let me know. we can arrange something, but it's not something I've been able to get so far.
Yeah, this is Craig Storms here. So anybody would like to see PiFinder, I own one and enjoy using it. It's been a lot of fun and really assisted my visual astronomy.
Great, thank you. Yeah. One of the features that I kind of like about it is if I'm looking at a particular object and I'm not sure what it is, maybe I just was panning around, I saw something kind of interesting, because it's got a catalog of 20,000 some odd objects, you can essentially say what is closest to where I'm at and get a list of things. It's actually got Palomar sky survey plates for all of the objects, so if you want to see what they may look like, you can reference that and see it right on the screen. So I use that quite a bit if I'm just sort of find myself observing without a solid plan. I'll just say what's nearby or what's interesting, and can kind of get a good night of observing even if I haven't done as much homework as I should have.
Yeah, I can add to that the Star Party people like seeing the picture in the little screen, so they get an idea what they're supposed to see in the eyepiece. Very nice.
Thank you. Thank you.
Richard, there's a couple questions in text, I think.
Oh yeah, I might have missed a couple.
Yeah.
Yeah. So I talked a little bit about alignment. Essentially, you put it on your scope, point your telescope at a bright star. The PiFinder will display a star chart essentially of the area around where it's pointed, and you can zoom in and out. You can turn the constellation lines on and off, but essentially you just need to recognize the star that you've selected to point your telescope at, and then select it on screen, and that lets it register the sort of alignment between its camera and where your telescope is pointing. And that's it'll store that, so if you put it on the same scope repeatedly, these dovetails do a pretty good job getting it aligned. But if you move it to a totally different scope, you'll probably want to go through that couple second process of just pointing it at any bright star, and then selecting that bright star on the screen.
Great presentation, Richard. Man, what a great meeting for presentations. Thanks to both you guys, Lucas,
Well,
Richard.
thank you.
Yeah, thanks for taking the time, not only to prepare, but to join us tonight. Really appreciate it. Fantastic presentations to both of you.
Well, thank you for hosting. Always appreciate it. And I'm a member of the Los Angeles Astronomical Society, by the way. So I hope that we will cross paths. Anyone here who's going to local events or star parties, if you see me, say hi. I love talking to people, so I hope to meet some folks.
Fantastic. Just curious, do you guys have a star party? And when is it? Do you host one?
We don't host a big one. We have our dark sky nights up by Mount Pinos. If you're familiar with kind of the Grapevine, it's almost at the top of the Grapevine. You kind of head off. We have a reasonably dark site there. I like CalStar if anyone is kind of keen on getting a little bit further afield, and I'm almost always at the Golden State Star Party. But yeah, the Los Angeles Astronomical Society does not host a big event. Kind of wish they would, but it's hard to find a venue for that.
Yeah, understood. Well, thanks. I'm sure we'll see each other again. Thanks
Yeah.
again. All right,
Thank
with
you.
that, guys, I think we'll conclude the meeting. Thanks to everybody who was here. Appreciate it. And this will also be posted on YouTube for review or to see for the first time. Thanks, everybody.
Thanks.